Now I want to look at a number of different polynomial functions and apply some of the characteristics that we've talked about and expand a little bit into talking about imaginary zeros. So let's look at the first row and look at the degree of the function. Notice that this is x plus 2, x minus 1, x minus 2. If I were to multiply this out, it would be x times x times x, which would give me an x cubed function, which means the degree is 3. If I look at this, I have an x and I have an x squared. So also, this would also be a degree 3 if I multiplied it out, because it would be x plus 2 times x minus 2 times x minus 2. Here I have an x to the third power, once again a degree 3. And here I have an x times an x squared, also a degree 3. Now what I wanted to point out to you on this is that there are a lot of different shapes that a degree 3 polynomial can have. We can have two really distinct turns, two really distinct bends, two distinct vertices on the graph, or we could just have a little bend or hardly any curve at all, and they're all degree 3. The way that we can distinguish a degree 3 from just a linear graph, degree 1, is it's not perfectly straight. So we know it has to be at least degree 3 if we see a bend in it like that. Now let's look at the types of zeros we have. We notice here on the first graph that we have 3 distinct x-intercepts. To be all x-intercepts are real zeros. That means we have 3 real zeros here. Now looking at the way and we can actually read these numbers off the graph and see that it's -2, +1, +2. -2, +1, +2. These correspond to the 3 numbers that would make each factor equal to 0. So if I put in -2 for x and multiplied this whole thing out, it would equal 0, because I would have 0 times -3 times -4, but it would still equal 0. If I put 1 in here, I would end up with 3 times 0 times -1, but the whole thing would still be 0. If I put 2 in here, I would have 4 times 1 times 0. The whole thing would still be 0. Because remember, zeros make the y value equal to 0, or the output of the function equal to 0. So this is a pretty easy one to figure out the zeros of. Now the second one, we see a place where the graph crosses the x-axis and a place where it just touches. Whenever the graph just touches the x-axis, that clues me in that I have a double zero, or a zero that occurs an even number of times. In this case, we see a double zero. X minus 2 times x minus 2 means the number 2 appears as a 0 twice. So we would list our zeros as -2, +2, +2. So there are still 3 zeros in a degree 3, it's just that some are repeated. So we still have 3 real zeros, but one is a double zero, or we would say a zero of multiplicity 2. When we go to the third one, we see that we have a triple zero. When the graph changes from being concave down to concave up right here on the x-axis, that means we have a zero that repeats an odd number of times. So this is an odd number of repeated zeros. In this case, it is a zero that repeats 3 times. So we would say the zero is 2, 2, 2. 3 real zeros, or we could say one real zero of multiplicity 3. Or we could say 1 triple 0. So we say 3 real zeros in that we have 3 factors, but they're all the same. So it's a repeated 0. It counts as all 3 though. That counts as the 3 zeros for our function. Okay, now we have a place where the graph crosses the axis straight across. So it doesn't go down and touch, it doesn't curve as it goes through. So this is just 1 0 here. So this gives us 1 real 0, x equals 2. 1 real 0. I have to have 3 zeros altogether, so that means the other 2 have to be imaginary. So the other 2 must be imaginary. So that's how I figure out imaginary zeros, is I figure out how many total zeros I need, which is the degree of the function. I account for my real zeros, and anything left over has to be imaginary. And remember I said that imaginary zeros occur in conjugate pairs, so they're going to be in pairs. So don't look for a single imaginary zero, look for a pair of imaginary zeros, or 4 imaginary zeros. So how do we find these imaginary zeros? We have x squared plus 4. Well, we know that x minus 2, if we set this factor equal to 0, we get x equals 2. If we set x squared plus 4 equals 0, we get x squared equals negative 4. Well, if we take the square root of negative 4, we get an imaginary number. Specifically, we get 2i. And since we're doing the square root of both sides, we're going to need a plus or minus here. So we're going to say that x equals plus or minus 2i. Now, for those of you who maybe don't remember why that's equal to 2i, remember that the square root of negative 1 equals I. So when I have the square root of negative 4, that's the same as the square root of 4 times the square root of negative 1. So that would give me 2i. And since I'm taking the square root of both sides, I have to account for both the positive and negative version of that. Okay, now let's move on. So those are a lot of examples of third degree functions with either 3 real zeros, 2 real zeros, one of which is repeated to make 3 altogether, 1 real zero that is repeated 3 times, or 1 real zero and 2 imaginary zeros. Now let's look at some an even degree function. So notice both ends are pointing the same direction, so this has to be an even degree function. We see here we have x times x times x times x, so we have an x to the 4th. This is a 4th degree function. Here we have an x squared times an x squared, so this is also a 4th degree function. So this W shape is a very common characteristic of a 4th degree function, but as we'll see, they're not all that shape. Here we have an x times an x times an x squared, once again a 4th degree function. So let's look at these 3, and then we'll go down to the last line and look at those. So here we have 4 separate real zeros. It can be easily read from the graph, or you can also look at the 4 factors and determine what those zeros are. We have to have one that's negative 1, one that's positive 1 that goes with the x minus 1, one that's positive 2, one that's negative 1, and one that's negative 2. And you can clearly see that we have 4 real zeros, which means we have 0 imaginary zeros because we've accounted for all 4 of our zeros. Now if we look at the next one, notice we have 2 places where the graph just touches. So that means we have 2 double zeros. We have 2, 2, negative 2, negative 2, based on our factors here that we can see. So once again, we have 4 real zeros. We have 2 double zeros is what we have. 2 double zeros. And then we have 0 imaginary zeros. And remember that word can also be the word 0 can also be the root. We can say we have 4 real roots and 0 imaginary roots. Now when we look at this next one, notice we have 2 places where the graph goes straight across. So that means we only have 2 real zeros. And we can see that they come from these 2 factors, 2 and negative 2. So we only have 2 real zeros. We need 4 altogether, so the other 2 must be imaginary. The other 2 must be imaginary. Now some students go, well, how do you see the imaginary zeros on the graph? Is it where the curves are? No, you cannot see the imaginary zeros on the graph. You just have to know that if you don't have enough real zeros, the other ones have to be imaginary. Now if we look at this third factor, we can see where the other imaginary zeros come from. If we take x squared plus 1 equals 0 to solve for the other values of x that would make our output equal 0, x squared equals -1, x equals plus or minus the square root of -1, so x equals plus or minus I. So I and negative I are my other two zeros, my two imaginary ones. Okay, let's go down to these two. Now these are kind of odd looking things. Let's look at their degrees. Notice here we have an x squared and another x squared. So this is a degree 4. And you can see that it kind of looks a little like those W shapes, only the W isn't fully formed. It just kind of curves. So it only changes direction once. It kind of curves and it changes direction once. But it does have that kind of a shape that we can sort of see a hint of where a W sort of shape might have been. Let's look at what's going on with this. Notice that we have one place where the graph touches. So this is a double 0 here. It actually could be, technically could be any even numbered multiplicity of a 0. But in this case we can see that we have an x minus 2 squared. So we have two zeros that are real numbers, but the other two have to be imaginary, and we can see the same factor that we just saw in the previous. Our other two zeros are I and negative I. So 2 real, it's a double 0, and 2 imaginary. Now the last one looks a lot like a parabola, but it is not a parabola. This is an x squared times an x squared. This is also a 4th degree. So interestingly enough, a 4th degree graph can look very distinctly like this W shape, but it can also look like any even function that is a degree lower. So the next degree lower that's even is x squared. So this graph could look very similar to a parabola. And this one's kind of a halfway between the two. So we could have anything from, so those are kind of the variety of shapes that we would see with a 4th degree function. Now we could also have a really distinct W shape where the W wasn't even, so we could also get something that maybe looked like that, you know, where the W wasn't symmetric, but it still had sort of that W shape. Now with this one, all the zeros must be imaginary because there are no x-intercepts. No x-intercepts. That means all zeros are imaginary. So it must have 4 imaginary zeros. And we get 2 from each factor. So 4, I should say all 4 zeros are imaginary. So I think I'll just put it in there. All 4 zeros are imaginary. So we know we had this factor earlier and we found out that this gave us positive 2i and negative 2i if we set it equal to 0. If we set x squared plus x plus 1 equal to 0, we would have to use the quadratic formula. So I'm just going to do this really quickly. A would be 1 because this would be 1x squared, and then b would also be 1 because this would be 1x, and c is 1. All three numbers are 1. So using my quadratic formula, x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. You're going to learn that song if it kills you, if it kills me. Okay, so I'm going to substitute a 1 for b and for a and for c. So I'm going to have x equals negative 1, plus or minus the square root of 1 squared minus 4 times 1 all over 2 times 1. Which gives me negative 1 plus or minus the square root of 1 minus 4, negative 3, all over 2. Now, the square root of negative 3 is just the square root of positive 3 times the square root of negative 1. So I'm just going to write that up there, square root of 3 times the square root of negative 1. So it's the square root of 3 times I. So this is going to give me 2 more imaginary numbers, negative 1 plus or minus the square root of 3i all over 2. So this gives me 2 different solutions. Negative 1 plus the square root of 3 over I plus the square root of 3i all over 2, and negative 1 minus the square root of 3i all over 2. So these would be my other 2 zeros. Now you might think, wow, that's a weird looking number. I just want to demonstrate to you that this actually is a zero of this equation. So I'm going to pull up my graphing calculator and just put that in there and show you that it does make the equation equal to 0. I went ahead and typed in my value and stored it to the variable x. And I want to show you where I get, if you click on the pi button, that's where the I comes from. Now I'm going to type in my equation. So if I type in x squared plus x plus 1, notice the bold because it's picking up a variable that I've stored, times, and then I have x squared plus 4. Notice I get 0. That means when I substitute this number in for x into the equation, I get 0, which means this number is a 0 of my graph, or of my equation, sorry. And if I do this again with the negative version of it, now I'm not using the negative, so I'm using subtraction here. And then I go back and grab my equation. That also gives me 0. So just to show you, that actually works. Now back to the notes for the big idea. Factors and zeros. If x equals a is a 0 of a polynomial, then x minus a is a factor of the polynomial. So for example, if we have a 0, or an x-intercept in this case of -3, the factor would be x minus a -3 or x plus 3. The same thing is true for imaginary numbers. So if one of my, so for example, this second to the last example could be written as x minus 2 times x minus 2 times x minus I times x plus I. That would give me, that would take each one of these zeros and turn it into a factor. X minus I times x plus I, if I multiply this together, gives me x squared plus 1.